So in this linearized Kleiber's law relationship, what you're seeing is a graph of the logarithm of the weight, the mass of an organism, and the logarithm of the amount of calories that it burns in a given day, its basal metabolic rate. And if this is a linear relationship, then you can transform the regression equation to make C the subject. And just to go over that little bit again here. So the linearized equation that Excel has kind of come up with in the regression here will give us log of C is 0.7502 times log of W plus 1.8323. And just real briefly, those groups that worked on this, how did you solve this equation to make C the subject? How do you rearrange this to get the C by itself?
Well, you have to get the log out of C.
Uh-huh.
So the actual equation would become C equals base 10 raised to the power of basically everything that's on the right side.
Yeah, everything's on the right side. Right, to get the log out of a quantity, if you like, just use it as the exponent with the base, the corresponding base, as the base. So since these are base 10 logs, we'll use a base of 10, and then that gets C by itself. Because by properties of logarithms, 10 raised to the power of log C is equal to C. All right, and then the instruction that says simplify to the extent possible, let's just real briefly do the simplification on this. I have an addition up here in my exponent. What can I do with that addition to simplify? Yeah, if we bring that arithmetic out of the exponent, addition in the exponent becomes multiplication of powers. So when I bring that exponent arithmetic down, I get multiplication by 10 raised to the power of 1.8323. Then we also have up here multiplication going on, 0.7502 times log W. When you bring multiplication from the exponent level to the power level, it becomes exponentiation. Right? It's a little caret, a little up arrow, if you like. So this multiplication going on upstairs, we can turn into either 10 raised to the 0.7502 raised to the log W, or, because that's not very useful, if we wanted to simplify it better, what we could do instead is trade out the order of this multiplication. Instead of 0.75 times log W, let's make it log W times 0.75. Oops. So in other words, I'm saying turn it around to look like this, times 0.7502. And then do that same thing. Multiplication in the exponent becomes a power of a power. But what's 10 raised to the power log W? W, right. So, all told, we end up with this rather nice-looking W raised to the power of 0.7502 multiplied by 10 to the power 1.8323. What's 10 raised to the 1.8323 about? Did you do this step? It's like 67 point something. 0.9672, so we'll make it 67.97. Okay. All right, so that's the rearrangement step, the rearrangement and simplification step. You're not going to get your relationship between C and W to be much simpler than this one. And all it was to undo the log, to rescue the C from inside of the log, just use those expressions as exponents with a power of 10, a base of 10. And then for the simplification, just take all the arithmetic that happens in the exponent and bring that arithmetic down by escalating it a level. Addition and subtraction upstairs become multiplication and division downstairs. Multiplication and division upstairs become powers and roots downstairs. So now we have our expression for C versus W. But I didn't want to wrap up our review today without talking about this interpretive question, part B rather. So read through this for a moment. True or false? And why is it? The slope of this equation indicates that for every kilogram that a mammal increases its mass, its body mass, it will require 0.7502 additional calories in order to sustain itself. Is that a true statement or a false statement?
The equation are the law functions.
Okay, so there's a tip-off, right? That this linear graph is not a graph of W versus C, it's a graph of log W versus log C. So that's a good reason to call this false, right? That the slope here is a measure of the relationship of log of C to the log of W. So we could say it like this. We could say that the slope here is measuring the ratio of a change, a difference, in the log of W divided by ratio of a change in log W to the change in log C. And not what is written here in the sentence looks like a change in C. I'm going to call that delta C. We're going to use that notation next week. Versus a change in W. Whoops, I guess that's backwards. Change in W right there, change in C there. So this is a false statement, because the slope is a measurement here of the relationship between the logs of these quantities and not between the quantities themselves. So how do we fix this? How would we interpret this 0.7502? So if we want to patch this up, let's just run with the same way that we always write down a slope and when we interpret it. That we say for every increase of, and in our denominator here, 0.7502 over 1. And the 0.7502 is a change, an increase, in the log of our vertical variable C. This 1 is a change in our horizontal variable, log W. So for every increase of 1 in log W, so here's where we're adding what we need to add in order to make this an accurate statement. We're adding the word log here. For every increase of 1 in log W, there is an increase of 0.7502 in not C, but the log of C. Again, we have to add those logs in there before it becomes an accurate statement. But let's take this accurate now statement and let's rephrase it so that it tells us how W and C are changing and not how their logarithms are changing. In other words, when I add 1 to the log of W, so when I go from, let's say, 0 to 1 here, what am I really doing to W itself? For the hint, let's go over here. Oops. If log W is changing by 1, how much? What's W doing? How do I solve that for W? To get rid of this log. So, to get rid of that log, we just make it a power of 10. And we end up with 10 to the power 1, which is equal to 10. But because we shifted from linear thinking into logarithmic thinking, we also have to shift our arithmetic from an increase in amount, as we were talking about before, to an increase in percentage. In other words, instead of addition and subtraction, we want to be talking about multiplication and division. So instead of saying an increase of 10, we need to say an increase by a factor of 10. So that's how we're going to change the verbiage here. Every time the body mass of an organism increases by a factor of 10, there is a corresponding increase in their calorie consumption, or their calorie production, if you like, by, again, make 10 the base here, 10 raised to the power 0.7502, and there is an increase by that factor in the calories consumed. Someone with a calculator, can you tell me what 10 raised to the 0.7502 is about? 5.626. Okay, so reading this sentence that we have here. Every time a mammal's body mass increases by a factor of 10, so if something weighs 10 times more than I do, has 10 times more mass than I do, then that thing will require 5.626 times as many calories as I do. Let's just quickly look back at the data that's in the table and verify that what this would mean. Let's suppose I had an animal whose mass was 100 kilograms. About, 220 pounds? That animal is 10 times more massive than this animal that weighs 10 kilograms. So how many calories are they going to require? When the mass goes up by a factor of 10, the calorie consumption goes up by a factor of 5.626 that we saw down at the bottom. So to figure out this animal's calorie consumption, just multiply 382.4 by that 5.626. And what do you get? 2151. Let's leave it at 4 sig figs right there. Okay, 2,151. So again, what the slope is telling us is it's telling us how these changes relate to one another in this relationship. And both of these changes are multiplication changes, multiplicative changes, because our linear relationship was found on a log scale.